first, we will look at how a general optimization problem looks like. We work here with n-variate polynomials of degree d, and x here, everywhere. Can you actually, just a moment. Just a moment. I'm trying to see something so that I can myself see better what I'm showing to you. Yes, so x here is a polynomial in n variables, and the total degree of the polynomial is d. Here, for example, n is 2, bivariate polynomial, and d is 2. And we will work with the polynomial optimization problem, which involves polynomials p and g1 to gm. And we will introduce the set S. It will go with us through the whole presentation. And this set is the set of all x's such that g1 to gm are non-negative. And our goal is to find the minimum of p on S. This is a very short problem, which looks very simple, but actually this is not simple at all, because it is a very general problem. There is a lot of applications which you can formulate in this way. And in fact, just in this formulation for general polynomials, one cannot solve it. So we have to do something with it to be able to solve it. And today we will do a very particular thing. There are many ways, many approaches which you can use to solve or approximate these problems. Mostly you approximate them. It's not very frequently the case that you can solve them exactly. But all these ways are in a way similar. And the approach we will look at today, it goes like a red line through almost all existing approaches. That's why I decided to talk about it. So we first rewrite our problem using the lower bound approach. Instead of just minimizing p on S, now we are interested in finding the best lower bound for p on S. So lambda is our lower bound. And to say that it is lower bound, we have to say that p minus lambda is non-negative for all x in S. And to say that this is the best lower bound, we have to maximize it. These two problems are equivalent because through the minimum of p, we can construct exactly this lower bounding hyperplane for p. And now, instead of our initial problem, we will look at this problem. And this problem has the advantage that instead of something which is quite abstract, which we had at the beginning, we obtain a problem with a particular question. Namely, now we have to answer the question of when some polynomial, in our case p of x minus lambda, is non-negative on some set, in our case x. If we could characterize in some explicit way all polynomials which are non-negative on a given set, we basically could solve this problem. Of course, since these two problems are equivalently hard, we cannot just answer this question. This question is extremely hard. However, there is another question which we can ask, and this question turns out to be easier, and this is the question which we will consider. To make it more illustrative, we first will simplify the set. So before we had the set S, which was defined by a bunch of polynomials non-negative for all x's. And now I just say that, okay, instead of set S being somehow restricted, I take S being the whole Rn. So I only can write it as 1 is non-negative. So it always happens for all real numbers, for example. And this set is simpler. And for this set, we can observe the following. For example, instead of saying that p of x minus lambda is non-negative, we can say that p of x minus lambda is equal to a sum of squares of polynomials. And clearly, the sum of squares of polynomials is non-negative. So by rewriting it in this way, we obtain some valid lower bound lambda, because p of x minus lambda will be always non-negative. However, we cannot guarantee that every non-negative polynomial can be written as a sum of squares of some other polynomials. And as a result, instead of the very best upper bound, we obtain some upper bound. And so when we do this rewriting, there are basically two questions. Question number one is, did we really get anything easier, or we just rewrote one hard problem as another hard problem? And question number two, this inequality sign, does it really make our bound worse, or it actually allows us to obtain very good bounds, or maybe even the optimal value? So next we will look at both of these questions. The first question is about how hard the new problem is. The new problem is actually way easier. So while I said that the first problem was impossible to solve in general, the second problem, the problem with sums of squares, is solvable in polynomial time up to any precision we wish. So we actually obtain something which we can deal with just by replacing non-negativity by sums of squares. And before going to the second question, namely how much do we lose if we do this replacement, I will show why actually it is easy, well, relatively easy, to solve a problem involving sums of squares. So this is our initial problem. We have rewritten our upper bounding problem with lambda, sorry, lower bounding problem with lambda using sums of squares. So now we will find some lower bound lambda such that p minus lambda is equal to sigma, and sigma is a sum of squares. To be able to solve this problem, to make it really solvable, we have to restrict the degree of the sum of squares, because otherwise the degree can be infinite, and dealing with infinite degree problems, we still really can't. So we restrict the degree, but let's say we restricted the degree, we obtain some result. If we don't like this result, we can always make the degree larger. So this restriction is not so crucial. Now, after restricting this degree, we can show that our problem with the sum of squares can be actually rewritten equivalently as an SDP program. An SDP program is a linear program which involves a constraint that some matrix is semi-definite, positive semi-definite. Here is this constraint. Here is a reminder of the definition of a positive semi-definite matrix. And you can see that actually, indeed, this is a problem where we need to find a constant lambda and a matrix M. Everything is linear in this constant lambda matrix M, and this matrix is positive semi-definite. So it satisfies the definition of an SDP. And as you can see, a positive semi-definite matrix is a matrix for which its quadratic form is always non-negative. So here we can observe that there is a quadratic form of M with a certain vector. So basically this constraint is equivalent to saying that P of x minus lambda is equal to something non-negative. So from this, we can already see that whatever we obtain is, again, some valid lower bound. And the interesting moment here is that this bound is exactly the same as the bound above. So saying that P minus lambda is equal to sum of squares of degree 2D is equivalent to writing it in this form, where this MD is just a vector of monomials. So a vector of monomials up to degree D. And here is an example. If x is x1, x2, and d is 2, a vector of monomials is just a product of x1, x2, such that the degree of this total product is not larger than d, not larger than 2 in this particular case. So as long as we have relaxed our hard problem, which we had initially, to our not so hard problem, which we have now, and which involves sums of squares, we have obtained an SDP, and we can solve an SDP, because for solving SDP, usually an interior point method works well. Also, alternating direction methods of multipliers work well. And there are state-of-the-art solvers which can solve SDPs very well, or you can write your own solver. So solving SDPs now is not something that that is impossible to do. It's something which one can even write on their own. Now, our second question was, how much do we lose by moving from a hard problem to a not so hard problem? So this inequality sign, how bad is it? And this question, namely the question of how are non-negative polynomials connected to sums of squares, is a long-standing question. And people have been thinking about it for a long time because it seems quite intuitive that they must be strongly connected. And the result, which is like the main result, the most general result which have been obtained, looks like this. This is a theorem by Artin from the beginning of the 20th century, who said that any non-negative polynomial can be written as a sum of squares, but not as a sum of squares of polynomials, but as a sum of squares of ratios of polynomials. So it is a more complicated object than just polynomials. And this hints that our relaxation, when we just move from non-negative polynomials to sums of squares, not sums of squares of ratios, must sometimes be not so good. And let's look at it next. So first, indeed, sometimes it will be not so good. And here is one of the examples. This is basically the example of the first polynomial, which is non-negative and which is not a sum of squares, that has been obtained in the literature. This polynomial is called Motzkin polynomial. And it is a polynomial just in two variables and degree 6. And it is non-negative by the arithmetic geometric mean inequality. Here is an arithmetic mean of 3 objects. And here is a geometric mean of the same objects. So the arithmetic mean is larger, so the polynomial is non-negative. However, it can be shown just by looking at the degrees of these monomials here, that there is no way that this polynomial can be a sum of squares. And actually, even writing this polynomial as a sum of squares of ratios of polynomials is not so easy. This pretty small polynomial requires 4 not so easy ratios to write it. So there exist polynomials which are not sums of squares and which can be not so easy to approximate by sums of squares. Therefore, in the perfect case, what we would like to do is we would like to replace our p of x minus lambda non-negative by p of x minus lambda is equal to sum of squares of ratios. And we can deal with the denominator, rewriting it using semi-definite matrices. We can deal with the numerator, rewriting it as a sum of squares of semi-definite matrices. But then we have a ratio of semi-definite matrices. And unfortunately, with this problem, there is no way that you can really go around it. So this problem is hard and very rarely used in the literature. Like, you can do some tricks and things, but in general, it is not very useful so far. Maybe some people will soon show how to use it. But so far, we restrict ourselves to sum of squares. And although indeed sometimes we lose if we get something like this Motzkin polynomial, which is not so easy to write as a sum of squares, even as a sum of squares of ratios. But in many cases, we do not lose much. So in particular, even Hilbert, before Artin, has already shown that some groups of polynomials can be written as sums of squares, and they're non-negative if and only if they are sums of squares. So we don't even need ratios in this case. In this case, our rewriting as a sum of squares is equivalent. These are only 3 cases, unfortunately. In all other cases, what we hope for is the following result. This result says that every non-negative polynomial can be approximated by a sum of squares. It can happen that this sum of squares has to have a huge degree, and it is only approximated well when this degree goes to infinity. So in practice, for example, our bound will be not so good, but this is rather an exception. So in real life, if you need to solve this problem and people just replace non-negative polynomial by a sum of squares, usually they obtain pretty good result. Not always optimal, but pretty good. So basically this result by Berg, it is quite strong. And there exist even particular forms of these sums of squares, which are considered the best to use in this case, which can converge well or which are good for optimization purposes. So that is it about the connection between non-negative polynomials and sums of squares. But how we started our presentation is with the set S, which is the set where some polynomials are non-negative. And the set is not just Rn. The set is a subset of Rn in our case. Actually, here X should be in Rn. And for this set, there exists a very similar result. So if our set is not Rn, but our set is something more complicated, but that we can write it using polynomials, then we can use the following. We can write our non-negative polynomial as some sum of squares plus an additional term. And a sum of squares is, of course, always non-negative. And the additional term consists of some other sums of squares multiplied by our polynomials, which define our constraints. So as a result, as long as these GIs are non-negative, this whole product is non-negative, and this whole term is non-negative. So again, this whole thing is always non-negative on S. Therefore, if we substitute in our problem, we're going to find the lower bound lambda for P on S. And now we substitute instead of non-negativity constraint here the condition from above, the result of Putinaar's theorem. Then we still obtain a valid lower bound. And moreover, basically, it follows from this theorem that if our set is compact and some other very not hard to impose, like easy Archimedean condition holds, then at some point, at some d, if we increase d large enough, then actually these two problems will become equivalent. Well, in some cases, d can go to infinity, but in some cases, d actually can be finite, and then you really can rewrite a hard problem of non-negativity as a not so hard problem of sums of squares. And this is basically the process of increasing this d and obtaining some bound lambda for every d is called constructing a hierarchy. And this hierarchy is the hierarchy of the resulting lambdas, which we obtain. And this particular hierarchy, which results from Putinaar's certificate, is called Lasserre's hierarchy. This is the most typical, the most popular tool in polynomial optimization up to this moment. So for now, basically, we're going to end up the section of the theory. I will wrap it up, and then I will ask if there are any questions. So to wrap it up, let's recall that we have rewritten a problem which was a polynomial optimization problem over a general set defined by polynomials as its lower bounding equivalent. Then for this lower bounding equivalent, we used sums of squares to replace the condition that some polynomial is non-negative on some set by the condition that some polynomial is a sum of squares on some set. And this condition is the one which provides us with good bounds, and these bounds in general converge to the optimal value of our problem. Moreover, there exist ways to extract solutions. So we not only obtain a bound, but in many cases we can extract either an optimal solution or some close to optimal solution. However, this bound, if you maybe remember, is constructed using semi-definite programming, and the size of the semi-definite matrix used in this bound depends on the number of monomials in the problem. The number of monomials in the problem is d plus n choose n, where d is the degree. So our SS would be degree 2d. And n is the number of variables. So as long as we want to obtain a better bound, so we want to increase the degree, or we want to increase the number of variables in our problem, this number of monomials becomes huge. It grows exponentially. And at the same time, the existing solvers, which are really like well-developed solvers, they can deal well with SDPs of the size like up to 500, maybe even 400. So as a result, probably you have not seen many applications of polynomial optimization in real life problems, because it is just being developed now how to use it for larger problems than this, what we have here. Before, it was mostly used to show some theoretical results. However, right now there are tricks to improve the size, so we can deal with larger size. And most of the time what we do is we either use the fact that the problem is sparse, and then the semi-definite constraint becomes easier, or we use some symmetry or some other structural properties of the problem. And the two problems which I would like to present next, I think they actually can exhibit especially some sparsity. I'm not sure about symmetry. And that's what we're going to look next. And before we look at it, are there maybe any questions? And I hope I will be able to see it. Okay, so I see nothing. So I suppose that I can go on. Now, let's go to our problems. Just to make it clear, I myself mostly do theoretical polynomial optimization. But if I have to deal with applications, then the only application that I'm really familiar with is polynomial optimization in energy systems. So that is one of the problems where this problem is really used in industrial size. So energy system of industrial size can be dealt with using the tools which I have just shown to you. And therefore, that is the problem which I mostly work with. However, for this talk, I understand that the audience is mostly interested in machine learning and data science. And I was curious to find something in relation to these topics and not in relation to energy systems only. And I have found two applications which I myself found very interesting. And I hope you also will see something in it that will attract you maybe. So let's start with them. There will be two. The first one is an immediate consequence of what we have just done. So we have just replaced non-negative polynomials with sums of squares. And that is basically what we can do not only in the case which I have presented, but in some other cases. Here is a formulation of a very general problem, which even I, with my limited data science experience, have encountered quite many times. Namely, we have to find some function f that belongs to some given family of functions, and that minimizes our given convex functional plus some penalty term. And the functional usually depends on f evaluated in our data points or features which we make out of these data points. And the example which the first came to my mind was the elastic net regression, where as a family f, we want to find a function that belongs to a family linear in both features and parameters. And our functional here, L, would be the least squares operator. And our penalty term, omega, would be the sum of norm 1 and norm 2 of the coefficients in F. So this is a problem. This problem is nice. In particular, what is really nice in this problem is that we can deal with functions which are linear in both features and parameters. So for optimization purposes, like to solve elastic net, we have to solve an optimization problem. And this full linearity is very convenient because we already have this complicated penalty term. If we also have here something nonlinear, it becomes harder. However, there are cases where using functions which are absolutely linear, both in features and parameters, is not so easy. For example, a very popular example is estimation of density, because if we would like to estimate a density, then we have to consider our family F, which consists of non-negative functions. And therefore, we cannot just use the linear functions because they will be trivial. So what people use is, for example, kernels. And then they assume that the initial function is a kernel, and then they choose the functional which has to be minimized, for example, log likelihood loss, and a certain restriction on what type of a distribution we want reflected in omega. However, kernels, of course, they have their own restrictions, and they have their own non-linearities, or you have to restrict yourself to a particular family of kernels, and you're not sure if that's the best family. So it is always good to have some alternatives. And there are various alternatives, and today we will look at this manuscript, where the alternative suggested basically is the following. Assume we have a problem with our family calligraphic F being non-negative functions. Now, we recall that any function which is a sum of squares is non-negative. Moreover, any function which is a sum of squares can be written using this semi-definite matrix A. And here are the vectors of monomials. So, okay, we can do that. But also what we can do is we can say, okay, we replace vectors of monomials by vectors of features, whatever features you would like to have. This will be still a valid non-negative function, just because A is positive semi-definite. And this function is still linear in A. So it stops being linear in the features, but it is still linear in A, and A in this whole problem becomes our optimization variable. So it is very good for us that our optimization variable is still appears in some linear way. And basically what the authors show in this manuscript, and which what I found pretty exciting, is that first, this is a convex function of a very nice form, and basically it preserves convexity of L. So as long as L is convex, which is the restriction we use, by substituting this function in this operator, we do not lose convexity, and in this way it is similar to the linear function in both parameters and features. And the second thing is that if we use these type of functions, we still have a representative theorem, which means that our optimal function can be written as a sum of some basis functions multiplied by some coefficients. And the basis functions which we have, and which, how to say it, the basis functions and these coefficients, this whole thing, basically looks like some SDP matrix multiplied by something. And this SDP matrix becomes our unknown. And independently of how many features we had initially, this SDP matrix is always of the size, the number of the observations by the number of observations. Of course, the number of observations can be huge, and this SDP can be huge, but it is interesting that this representative theorem still exists, which is, again, very similar to the linear case. And it is interesting that the size is still bounded independently of how many features you have here. Of course, what is not bounded is how many of these matrices you will have. So the number of these SDP matrices will depend on the length of this vector. Why I think this could be promising is because potentially this matrix could be sparse. You do not have to ensure that all features are correlated with each other, for example. That is the first thing. And the second thing, although here we talk about SDPs, and before we talked about SDPs, for certain types of problems, including this one, there are ways to rewrite this SDP using some other types of convex optimization. And that's basically what the authors do in this paper. So if you're interested, you can have a look. There will be a list of references at the end. Basically, you can avoid using SDPs and use some other algorithm, which potentially can allow you maybe to deal with larger matrices in some cases. So that was the first case. And now our second case will be less straightforward in terms of applying SOS, but still pretty intuitive. In this case, we will talk about a Lipschitz constant of the neural network. As a reminder, a Lipschitz constant or a function f on a given set calligraphic x with respect to the given norm is the minimum constant such that for any x and y in our calligraphic x, the distance between f of x and f of y is not larger than L multiplied by the distance between x and y. In optimization, a function, so if this L is finite, so if we minimize and we really can find such an L, then the function f is called Lipschitz continuous. And Lipschitz continuity is frequently used in optimization as a stronger type of continuity, which also involves certain kind of boundedness. And it allows to, for example, calculate convergence ratios of some optimization algorithms and show that these ratios must be fast for this type of functions. Or it allows to show that what is the running times of a particular algorithm for a particular type of problem. Now, it turns out, at least to me it was interesting, because I didn't know about it before, that the Lipschitz constants are useful for neural networks in the following sense. How generalizable a neural network is depends on how high a Lipschitz constant is. So if the Lipschitz constant of this network is high, then this is correlated negatively with how generalizable it is. So in general, we want to have lower Lipschitz constants, which makes sense. It means that we want to work with a function which is in a way bounded and we have a certain control over it. Therefore, there are ways to basically bound the Lipschitz constant of a given neural network. So it is nice to take it into account when you build a neural network that the Lipschitz constant shouldn't be too high. However, to be able to bound it, we have to be able to estimate it. And for now, there are ways to find a lower bound on this constant. And I was looking for ways to find an upper bound of this constant because it's always nice to have an interval. And that's what we will look at next. Our neural network will be very simple. We just have, at every step, we weight our features x with some weighting vector w. And we have an activation function sigma. This activation function, we do not have actually any particular constraints on it. And our question is, what is the Lipschitz constant of the neural network, which is the Lipschitz constant of the last step of FT. And we will look at the upper bound. And I found two upper bounds in two papers. Again, we will see them in the literature list. These papers are manuscripts, as well as the previous papers. They're available on arXiv, but they are, I think, quite reliable manuscripts from the authors and from the quality of how they're written. So in our neural network, we assume that our output is one-dimensional for the ease of presentation. So, for example, we need to decide if the answer to something is yes or no. And we assume that X is convex, which, to my knowledge, is not a too restrictive assumption, but maybe I have to be corrected here. And our upper bound can be written as, notice actually here that we do not have any constraints on the type of the activation function. And these two papers are different in which types of activation functions they consider. And they basically cover all frequently used types. So what we can see is our Lipschitz constant can be bounded by some problem where the unknowns are in red A and B, 1 to BD minus 1. And if we look at everything here, then all these things are polynomial in A and B. This diag operator, it stacks BIs on a diagonal of a matrix. So it's just a matrix which only has a non-zero diagonal, and we have BI on this diagonal. BI is a vector. So we have to solve a polynomial, which is solve a polynomial optimization problem in A and B, which is exactly what we have been just doing before at the beginning of this presentation. And we know that to solve such a problem, we can basically rewrite it And here, initially we dealt with minimization, so we were writing it using lower bounding approach. Now we deal with maximization, so we will rewrite it using an upper bounding approach. So we will be searching for the best upper bound if we deal with supremum. And then we can use the SOS approach and Putinar's theorem, for example, as before. And we will obtain a valid upper bound on the Lipschitz constant of a given network. So here, of course, here, unfortunately, there is no way really to avoid SDPs. So you have to solve an SDP. However, neural networks usually have quite a lot of sparsity in terms of how the layers are connected. So in basically both of these manuscripts, people exploit sparsity as much as they can to show what is the largest size of the networks they can deal with. And so far, it is mostly a theoretical approach. These networks did not seem to me too realistic, but I think if people work more on it, maybe it will be possible to use it for more realistic neural networks. Also, sometimes to estimate a constant, you can simplify your neural network and say that, for example, the Lipschitz constant of your network is bounded by a Lipschitz constant of some simpler network, and then for this simpler network, you can use this approach, for example. So that is it about my applications, and basically we are moving to the end. In this work, I have told you about mostly the relation between polynomial optimization, non-negative polynomials, and sums of squares. However, there is another angle from which you can look at this problem, is the relation between non-negative polynomials and measures and generalized moment problems. Basically, a polynomial problem, a polynomial optimization problem is equivalent to a generalized moment problem. And this is another popular way to deal with this type of problems. And if you are more into statistics, more into measure theoretic approach, then I would advise to read this book, which will be also in the list of literature, which basically connects all three concepts. So polynomial optimization, sums of squares, and problems, optimization problems over certain types of measures. Because these things are, in a way, the same question. Now, I have talked about two applications, and I have also mentioned that I deal with energy optimization problems, but I would say there is way more applications. And recently, the ability of people to solve semi-definite programs grows, so new applications are emerging. And moreover, we have been talking about sums of squares, but sums of squares is not the only thing that is always non-negative. There are other polynomials which are also always non-negative and which you can use as an alternative to sums of squares and also obtain some tractable problem. So it's actually now a very active topic of research. What can we use instead of sums of squares? And also, of course, there are many ways to explore sparsity and symmetry. So if you're interested in these applied topics and which questions you can answer applied questions using polynomial optimization, I listed this survey there. It will be also in the list of literature. Please have a look at it. And I hope something there will answer your questions. And that is it for me. I am, again, very grateful for talking here. And thanks a lot for being here. And if you have any questions, I will be glad to answer them. Now, as to the list of literature, I suppose that the presentation will be uploaded to the website. So basically, the list of literature is here and there. But I suppose that it should be available through the video. But if it is not, then please let me know. I can share it in some other ways. Or if you're interested in anything particular, also please let me know. Now I will just, I guess, turn it off. And no, I should better not turn it off, because if there are any questions related to presentation, it's better for me to have it in front of me. So please just, if there are any questions, ask them. And if I don't hear you, also somehow let me know so that I can hear you.
Can you give a little description of energy optimization problem? What is it? And
yes. Let me maybe. Let me see how I can do that, because I even have like a nice description of it. But then I'll have to open. Do you think it makes sense to? I will be able to open another PDF file without destroying this one, or I better not go for so high risks? Okay, not clear. Then let's. I will then give it a brief description. So basically, what we usually have to do is that we have a problem we have an energy network with all kinds of generators, switches, transformators, which is placed everywhere, like geographically somewhere, and they're all connected by power lines. These lines which we can see when we are outside on the streets, and they are on these poles and they connect them, or they are under the ground. So all these lines, they connect our generators, and they're supposed to deliver energy to us and to businesses, companies, whatever. And of course, during the day, there are several tasks which you have to solve in relation to this energy system. And the task which is especially suitable for polynomial optimization, it is as follows. So every like 10 to 20 minutes, the operators in the systems, at least that is how I see it with the system that I have seen. Maybe it is different in different systems, but operators in the systems, they have to set up certain levels of voltages and powers on their generators, so that the system will deliver the needed level of electricity, and the generators are not overheated, that lines are not overheated, and that everything works smoothly. So to set up these values, we have to solve an optimization problem. Basically, this optimization problem is the problem we have to find these values of voltages and powers in the system for the operators to set up, such that nothing is overheated, everything is delivered to the customer as much as the customer needs, and that the system is in equilibrium. So initially, we need to correspond to a certain solution to a dynamic problem. This will be our dynamic constraints. And this whole problem can be written as a polynomial optimization problem. Is that a clear answer, or maybe I should expand more on it? You're welcome. Another text question?
yes, someone typed a text question, but it disappears quite quickly, so I am asking him to type his question again.
I see. Yeah, sorry. Yeah, I think I still could not see a part of it. Maybe I will now see it better.
Have you seen the question about Lipschitz norms?
No, unfortunately, I do not see it. Maybe it is.
So the question, if I remember correctly, the question was, do you consider other norms other than Lipschitz norms? Something like that.
Well, that would be good to see. So from maybe I'm supposed to move. myself closer to someone to see it. Because I think that, how to say, it seems like it must be something else, because in Lipschitz constant, there can be any norm. Like norm is really not restricted, so maybe that is what the question was about. Is there any way I can see from whom it was, so that I can pay particular attention to that particular circle?
It was from Yuri.
Uh-huh. That I cannot do. No, unfortunately, I still cannot see it. Yuri, I'm really sorry. Well, now I can see it. So can you maybe write it now? Or ask it. Just. Yes, the norm can be any norm which admits some polynomial representation. So mostly they deal with, well, you can deal with basically infinity norm, you can deal with norm 1, and you can deal with norm 2. It just, for each of them, there will be a little bit different representation, but here the norm, oh, what's going on? Good. Yeah, so the norm here is just like a norm, as long as we can do something with it to write it as a polynomial, or some relaxation of it as a polynomial. Yeah, it's pretty free. Are there any other questions? Thank you. Thank you. It has a certain feeling of humanity, I must say. Like it was not so intuitive, but actually it kind of makes you feel people more like people because of these circles. That's very interesting. So should we wrap it up then, or how does that work?